Hey guys, welcome to the next video on Diels Alder reactions. So in this video, we're going to be covering, we're going to be going a little bit more in depth about the Diels Alder reaction we covered in the previous video, right? Because it's not going to be as simple as the example you just saw, right? This is the most basic example we could do with Diels Alder. We're going to have to go a little bit more in depth here. And I left the molecular orbital diagrams here because we're going to need them in a second, right? So let me just clean this up a little bit. So in the previous video, I showed you guys 1,3-butadiene interacting with ethylene, right? Now, in reality, we don't really just do it with these two compounds because that's going to be a little bit slow, right? We want to speed the reaction up a little bit. So how are we going to speed this up? Before we even talk about that, I just want to say one thing about this diene. I drew 1,3-cyclobutadiene this way. You can see it looks as if it looks kind of cis, right? 1,3-butadiene can also look like this. Trans. These two conformers, right, because they have this little single bond in between them, we call this S-cis, S-trans. All right? And this may be a little bit kind of confusing, right? But this single bond, these exhibit free rotation. All right? So it's not like this example right here, where if I drew this double bond, because there's the double bond here, this single bond and the single bond won't rotate. So we do not have free rotation like this. You can't have free rotation between this conformation, which is actually cis, and this one, which is trans. In this case, that single bond in the middle allows them to have free rotation. The trans isomer, the S-trans isomer, is more stable than S-cis. In Diels Alder, we must use an S-cis isomer. This is not allowed to be used. The orbitals are too far apart, so we have to use S-cis. All right? And so one thing they like to ask on exams is which diene is more reactive in a Diels Alder. So the diene that's more reactive in a Diels Alder is always the one that's in the S-cis conformation. All right? And so one example of that, it could be a question like this. Right? We have to order these in terms of reactivity. Now remember, in rings, we can't rotate any bonds. And so you can see that if we look at where's our diene, it will be right here. And you can see that this is the trans conformation, S-trans. Now in this case, because it's in a ring, this bond right here cannot be rotated to get the S-cis. So it's locked in as trans. And since we can't use the trans one, this is the least reactive. All right? Now what about 2 and 3? Now 2 and 3 are right now in the S-trans conformation, right? Let me highlight only what the parts with the double bonds. Right, this is the S-trans conformation, but because they have this single bond right here and here, they are able to freely rotate into the S-cis conformation. Right, so let's draw them in the S-cis conformation. My technique for rotating bonds when it comes to dienes, I leave half of it the same. So I'm going to leave right here, that part the same on the right. So let's see. You're going to have this, and all you're going to want to do is flip this end. So you see, this bond is coming downward to the left. So to do a 180, kind of put it this way, right? Or looking like this. You can clean it up afterwards. So I'm going to put that bond up, which is this bond right here, and so that has the double bond. And then this bond right here is going to be coming off of it. And so if we want to clean it up, it's going to look somewhat like this. Same technique for 3. Keep half of it the same. This bond is pointed downward to the left, so put it a little bit upward to the right. Like I said, we'll clean it up later. And now that's going to be this bond, so we put the double bond. And now we have that other bond coming in, and it's going to be coming in inward, so this way. And so let's clean it up. So that's those two dienes. So remember, the S-cis is the one we use in Diels Alder, and both of these can adopt that conformation. The difference is you can see kind of how these two methyls are outward and these two methyls are inward. Now remember, because that diene has to actually get close and they have to have the orbitals overlap, it's much easier for the diene to get in there if there's nothing blocking it, right? So again, we're coming back to the idea of like steric hindrance from Orgo 1. So in this case, because this conformation has those methyls outward and it keeps this space free, you want to keep this space free, it allows it to get in more and it's more reactive. So this is the more reactive conformation. So less steric hindrance in front is better for a Diels Alder when we're talking about the S-cis. And this one is going to be the second most reactive because we already said this is the worst. So the order we would put this in is 1, 3, 2. Okay? And also just a side note, if you can keep something locked permanently in the S-cis conformation, it's even better. A quick example of that, although I'm not going to show it in a reaction yet, is this compound. It's a 5-membered ring with that conjugated diene. You can see that here's a diene. And because it's in a ring, the double bonds can't rotate. That single bond right here can't rotate, so we cannot get the trans conformation. So this is very reactive in a Diels Alder. All right? And so that's the end of that little side note, but it is very important, and they very well could test you on that. So keep that in mind. So now, let's get back to this example. So like I said before, we don't usually just use 1,3-butadiene and ethylene. You usually like to speed up this reaction because this is going to be a little bit slow. How do we speed up this reaction? Well, one thing that we do is we can use electron donating groups and electron withdrawing groups. Usually you'll see an electron donating group on a diene. So I'm going to just abbreviate EDG because we could use a couple of types and I'll show you them later. And on the diene file, we usually have an electron withdrawing group. So I'm going to put EWG for now. So what does the electron donating group and the electron withdrawing group do? Well, if we look, we said that the name is an electron donating group. So we're going to be putting electrons into our pi system, into this conjugated pi system. The withdrawing group removes electrons from here, right? And so you guys can see that all these molecular orbital diagrams, right? The more electrons we have, so if I put, let's say, electrons into this orbital up here, pi 3, that's a higher energy, right? So what electron donating groups do is they raise the energy of the HOMO. So electron donating groups raise the HOMO. All right, and so they don't just raise the HOMO though. That's the thing. We can't raise the orbital of just simply one. We can't raise the energy of simply one orbital. So I can't just, let's say, take the HOMO and shift it upward. What's going to happen is, and let me make some more space here, is it's going to raise this whole thing up. Let me not take that. it raises this entire thing up. All right, let me just bring this off to a higher starting position. What electron withdrawing groups do is they drop, or I don't know, let's just say lower the LUMO. And like I said, they can't just lower one thing, so they're going to lower all of it. All right, so something like this. So now let me bring back their starting positions. All right, let's get them back to a normal starting position. So why would we want to do this? What does this do? Well, we said that the HOMO and the LUMO are the orbitals that interact, right? So HOMO to the LUMO. It's much easier for the HOMO and LUMO to interact when they have a lower energy, when they have a similar energy. So if I drew this right now, this is the energy difference between them, the HOMO and the LUMO. If we can shorten that, it will make our reaction much faster. So let's think about this for a second. Our HOMO, and by definition, the entire molecular orbital will be raised with an electron donating group. So let's shift it up a little bit. And the electron withdrawing group is going to decrease the energy of the LUMO, and like I said, everything else with it. So let me just get everything. And so it's going to drop this a little bit. So now what's the new energy that we have between them? So I'm going to use it in a different color so we can see it a little bit easier. Let's pick orange. So now the HOMO and the LUMO, remember these two interact. The new energy between them is now that orange piece. So you can see the orange piece is much smaller than that red energy line I drew before. So this interaction now is much better and even faster for the reaction. Okay. So electron donating groups raise the energy of our orbitals. Usually we just say the HOMO, and the electron withdrawing groups lower the energy of the LUMO. So this makes the reaction much quicker. All right. What happens if we reverse them? So now what happens if we do this? Let me erase this and bring everything back to this starting position. So I'm going to swap these, and so now the electron withdrawing group is on the diene, and the electron donating group is going to be on the dienophile. Now generally, the electron donating group, we like to have it on the diene because the diene has more electrons than the dienophile, right? This has, if you look at the diagram, four pi electrons, sorry, right there. And we have 2 electrons in our dienophile. So the diene is usually more electron rich. The dienophile is electron poor. We like to have electron donating groups on our diene because it's already going to put more electrons into a system that has a lot of electrons. In this case, we're doing the reverse. We're putting a withdrawing group on a compound that has a lot of electrons. So what would the withdrawing group do? The withdrawing group, like we said, is going to end up decreasing the energy. So actually, let me just change the starting position. It decreases the energy of the whole, all the orbitals. Well, let's drop this guy down. Or actually, even before that. Actually, yeah, let's drop him down. I'll show you guys in a second. This guy comes down. The donating group is going to raise the energy here. All right? So now, in this case, the HOMO and LUMO are further apart. You can see now, we did the reverse of what we wanted to do. We wanted to bring the HOMO up and the LUMO down, right? So let me just redo this again. Let's bring him back to the starting positions. We wanted to make this guy this energy right here, smaller. Bring the HOMO up and bring the LUMO down. But because we have a withdrawing group now on the diene, it's going to drop this down. And then for the dienophile, it's going to raise this up. Electron donating groups always raise the orbitals. Electron donating groups always raise the orbitals. Electron withdrawing groups always lower them. So this guy comes up now. Now you can see that the energy difference is even larger. So this is going to slow the reaction. Before, these accelerate the reaction, right? And let me just say, on the diene, on dienophile. And so if we have an electron donating group on the dienophile, it's going to raise all the orbitals, but we want to focus really on the LUMO. And the electron withdrawing group on the diene, lower the HOMO. And so these accelerate. Oh, sorry. They just slow the reaction. Right? And so that's how these electron donating groups and withdrawing groups work. All right. Typically, we want to have the donating groups on our compound, on the diene, and the withdrawing groups, we want to have it on the dienophile. Right? That's going to speed up our reaction. So in the next video, we're going to be covering more of what groups are considered donating groups and withdrawing groups, and how they will work in a Diels Alder. All right, because it's going to do a little bit of a change in how we're figuring out the product. All right, so I'll see you guys in the next video.